Good evening and welcome to Winchester Cafe Sci, and a special welcome to those joining us for the first time. Tonight's speaker is an Associate Professor of Marine Sustainability and Founding Director of the Centre for Marine Sustainability at Solent University. An expert in maritime decarbonisation, he leads a multidisciplinary team delivering research and innovation to understand and address the global challenges facing our oceans. Taking a systems approach, research in the centre is discovering clean alternatives to fossil fuels used in ships, investigating the impacts of marine pollution, and studying the safety of those working at sea. Please welcome Dr. Laurie Wright.
Thank you. Well, good evening, everybody. It's lovely to be here in sunny Winchester again. It's been a while since I've been up here. Just had a nice wander around. Tried to find a coffee shop, couldn't find any. It's all boutique restaurants and expensive stuff, but there you go. I got here fine. William, thank you for the introduction there. Hello to everybody who's joining us online as well. It's wonderful to welcome you into the talk. So I've spent most of my life in some way near the sea or connected to the sea. I grew up on the south coast of the Isle of Wight, and I can remember summers playing on the sand, learning to sail. I'm actually now a qualified yacht master, but when I set foot on a boat, I tend to be sick quite violently, quite quickly. It takes about a day to get over it. Having a father as well who worked for Trinity House, the lighthouse service, for most of his career. And now as a centre director working in this space. It's something that's very dear to my heart. What I want you to do, and those online as well, I want you to do this, is to spend a moment to just look around at the stuff that is around us. We're quite lovely surroundings here in the Ark, and the library to our side, and the gallery, the coffee cups in front of you, the table, the furniture, the floor, clothes you're wearing. The chances are about 80–85% of those things, at least part of them, will have been on a ship at some point in their lives. Largely a hidden industry, one that we don't tend to think about. I don't think many people thought too hard and long about the hundreds of thousands of seafarers who were stuck at sea for more than 6 months at a time when COVID first hit. Cruise ships off of Biomass, people stuck out there for months. It's largely unseen. When it works, we don't think about it, we don't see it, it just happens. But 85% of all the goods traded around the world are traveling by ship. So put that in context. This is representation. I thought I'd try my hand at a bit of artwork. I don't yet call myself an artist, but I thought I'd try. Each one of those represents 1,000 TEUs. Now, a TEU is a standardized container unit, a 20-foot container. So when you see those big ships at sea, they tend to be in 40-foot containers, just to confuse matters. But we measure everything in 20-foot containers, half the size. This is 1 week in Southampton. 17,000 containerized units enter Southampton every single week. Could be TVs, could be cars, could be shoes, could be furniture. Whatever you could possibly think of, probably it's in one of those things. In the space of a year, that's close to 1 million containerized units entering just Southampton. And that's just containerized cargo. That doesn't account for things such as what we call the bulk cargo, so stuff that is not in a container. That's gravels, things like flour. It comes as a bulk cargo, it doesn't come in a container. Doesn't account for the passengers that are making their way through Southampton. Hundreds of thousands of them every single year. Again, goes largely unnoticed. Something I always find fascinating about ships, though, is if I wanted to send past Australia, right the way around the world, and for argument's sake, let's say this parcel weighed 1 kilo, which makes my life easier with the maths, but we don't call it 1 kilo. It is cheaper for me to send that parcel to Australia than it is to send it from the Isle of Wight to Winchester. It is less, especially now, given that a first class stamp went up to 95. When I bought some stamps the other day, for the first time in about a year, comic books are 4 rather than 6, what happened to the other 2? But yeah, 95 pence a stamp. Current shipping rates cost me about 60p to send my kilo to Australia in a container. Obviously, I would have to buy the whole container or part thereof, which is slightly more expensive, but on a weight per weight basis, it is still cheaper for me to send that 1 kilo package to Australia than it is simply to send it here. It's cheap. It's very, very cheap. Very efficient. As a mode of transport, economically, it's incredibly efficient. As I said, we don't tend to notice it until it starts to go wrong. Ever Given ship a few months ago ran aground, transiting, got stuck for a few days. The cost, 1.9 billion a day was the estimated cost as a result of that grounding. 1.9 billion, it's US dollars, it's not in pounds, so it's a bit less from what I think. But the scale of this operation, it might be cheap to move stuff, the sheer scale of it means we're moving billions upon billions of dollars of product every single year. It's also very efficient environmentally. We send something by air. Yeah, you don't really want to send things by air. It's really not that good. We send something by train or truck. Okay, it's better than air. In fact, it's actually about a fifth, sixth of actually the air footprint, mile for mile. A ship, even smaller. It's about a fifth of the truck. By weight travel, the ship is a very, very efficient mode of transporting stuff. And it's simply a product of the scale of the thing. Right? These things are huge. You don't really get a scale. If anyone's ever been on a cruise, you've probably got the scale of a cruise ship, that sheer size of these things. You're talking 24,000 TEUs on back on these ships. These things are enormous. They're huge. As I said, largely unnoticed as an industry, about 1 million people work in it. Interestingly, at the moment, one of the reasons we're experiencing difficulties in supply chains is a large proportion of sailors, seafarers, are actually Russian and Ukrainian. They make up one of the large proportions of the seafaring workforce. It's also one of the more dangerous professions you can get yourself into, surpassed only by forestry and deep sea fishing. As I say, largely unnoticed. The problem then, why do I do what I do? Shipping is so great, it's cheap, it's efficient, it's really easy to just move stuff around, fantastic. Why do we have a centre dedicated to marine sustainability? Poor prop. Unfortunately, it's kind of moved around a bit. You can kind of just about see it. Most ships run on this stuff. It's a heavy fuel oil. Before anyone panics, it's not actually a fire hazard, don't worry, it's not actually a fuel oil, it's representation of rock, but it's pretty much exactly the same. Heavy fuel oil. This is the kind of the dregs that are left when you've taken all the good stuff out to fuel your car. If you imagine trying to put that in your car, it's got the consistency of treacle. So if you put that in your car, it's going to gum it up pretty quick, it ain't going to burn. In fact, there's an experiment, I don't suggest you do it, so my colleagues quite happily will tell you if you dropped a cigarette into it, it would go out. So it doesn't burn. So you question even how these things actually burn this stuff. Well, first you have to have a preheating mechanism. You warm it up, you bring it up to temperature, and then it becomes with your liquid, and you can pipe it into your engine, and you can burn it. It's the draggy bit, it's the bit that's rubbish, it's left over. It's full of all the wonderful things like sulfur. Sulfur is not great for you. There's been a lot of progression in desulfuring fuel, taking it out in ships to make it a little bit healthier. But sulfur mixes with water, it becomes acidic, you get things like acid rain. It's not particularly great for your health. It's also very carbon intensive. So ships, ship engines. If we were stood in this room, this is a relatively small room. If you were comparing a ship's engine room, you're talking an engine, some of them up to like 24 cylinders at a metre bore. These things are huge. You can stand in the cylinder of an engine in a ship. They are that big. They are burning hundreds of litres of this stuff every single hour. Very carbon intensive. That's why the master's in there. Ships, we took the whole fleet, makes up about 2.5% of all global greenhouse gas emissions. If we take the wider maritime industry, so that's the ancillary infrastructure, the bit behind it, about 3% of all global greenhouse gas emissions. I sometimes find it's hard to imagine what that actually looks like. So put that in a bit of context. That would rank it, if it were a country, 5th in the global rankings, higher than Germany and higher than Brazil. Now, ships tended to be left out of our wonderful collaborations globally to address greenhouse gas emissions. Until relatively recently, until the Paris Agreement, ships, when they enter international water, don't worry about it. The same with aviation. Nobody really wants to take responsibility for it or wanted to. Understandably, it's a lot of emissions. That's not the whole picture either. Sitting behind that, is a whole infrastructure of fuel supply. It's been in the news recently. Diesel has just hit 199 point something a litre, pretty much £2 a litre. We'll start selling diesel in decalitres rather than litres, millilitres. Switch from gallons to litre when it hit pound a gallon. So I'm not sure we're going to go to this time. But there's a whole infrastructure that sits behind this. We have on our doorstep pretty much one of the largest refineries in the world. Forley, it's the second biggest by land area in the world, producing these fuels. Not by production, by land area. So they're a more intensive, compact. Forley's quite spread out, which is not very efficient in terms of its layout. It's pretty big. That, of course, has a whole series of emissions and energy and everything else associated with it as well. So it's not just the ships that we're concerned about. It's producing the fuel to go onto the ship. So what we would term in our speak as life cycle emissions, emissions that are associated with the life of the fuel. This becomes important in a bit. So the question that comes out of it is, what do we do about it? Just for a sense of scale, really, this picture, I like this picture. It just gives you an idea of the scale that you're dealing with here. We're seeing a twin prop there. The prop, one blade, is pretty much the height of one of the men there. That's the size of this thing. So the energy that's coming out of that prop is in the order of megawatts. You're talking like a power station on board ship to power these things. Huge, huge amount of energy. Oil is very efficient. It has a lot of energy locked up in it. That's why we burn it. That's why we like it. To put oil on a ship like this, you need to use somewhere between 5 and 8% of the whole space is taken up by fuel. That allows it to go kind of halfway around the world. In space, it's efficient, it's easy. We've done it for about 100 years. What do we replace it with? How do we replace it? There are some that would advocate going back to sail. That seems like the obvious one. Let's put sails back on these ships. Ply the trade winds. I'd like to see you ask any of our cadets at Warsash to sail a clipper these days. I don't think they'd be able to do it. There's a running joke amongst some of our cadets that they use their sextants on their cadet ship, and then once they come out the cadet ship, they never use it again. Those kind of skills they're pretty much gone. You've also got to question whether that's viable. If you want fresh bananas when you visit the supermarket, yeah, that's not going to happen. You get a bit of the doldrums, something goes a bit slow, let's add 6 weeks to your trade pattern, your bananas are now slightly mushy and rotten. Not great, not great. So it's really not a solution for most things. It's a solution for some things. This is the only bit of sciencey, graphy bit. I'll explain it. So we have lots of options. What you're seeing here is what we would term as kilograms of CO2 per megajoule of energy. So the joule being, if you took an apple, do that with it, that's 1 joule of energy. So it's a measure of energy. Megajoules are 1,000 joules. And kilograms of CO2, as it says, kilograms of CO2 emitted when you use that particular piece of energy. The thing that's slightly different here, it's not just about burning the fuel. So if I was to fill this up, it'd be roughly half a kilo in there, I would guess, of fuel. If I burn it, I get a certain amount per megajoule of the energy that's locked up inside that. Down the bottom there, MGO and HFO, marine gas oil and heavy fuel oil. So this is what we call heavy fuel oil. Marine gas oil is a bit more like diesel. Okay, so when you're getting close to port, you have to start burning marine gas oil because that stuff's so nasty that you don't burn it when you're near port. It's just horrible stuff. So as a reference point, taking into account all of those emissions that are associated with producing our fuel, we're down here somewhere. So marine gas or heavy fuel oil, somewhere around about 75 to 80 kilograms of CO2 for every megajoule of energy you're producing. That's kind of our reference point. Now, this is only CO2. There are lots of other things associated with this, things like particulates. So when we talk about particulates, we're talking about particularly PM2.5s, particulate matter smaller than 2.5 micrometers. So if you think about the thickness of your hair, that's about 70 micrometers in diameter, average human. So very, very small, passes into the bloodstream very, very easy. So it comes in the soot and things like that. So that, another byproduct of that also. So, but this is only accounting for CO2. Generally, deal with CO2, other stuff comes down as well. So that's our reference. Number of ships are moving this stuff, LNG, liquefied natural gas. We've been using it for 40, 45 years, quite happily in a number of ships, probably longer than that actually. Been very niche in the market. So if you ever see a ship with those kind of bulbs on it, that's carrying liquefied natural gas. Okay. So it comes back to natural gas. You'll see them a lot in Southampton at the moment. We're getting a lot of our gas coming in that ship. The way they work is they use what they call the boil off. So some of that gas, as it's being kept under pressure, it's kept liquid, but some of it will literally start to boil, captures that boil off and it powers the engine. Very, very similar to a standard combustion engine, but it's just using gas rather than diesel. Tends to be cleaner, Doesn't do a lot for your carbon footprint though. As you can see there, there's quite a range. Some shipping companies will claim, it's down here, it's better. If you get it right, then yes, it is better. The reason you see that big bar there is what we would term as uncertainty in there. It's one of those wonderful things in science. You're never sure about anything. You know, does the world really exist? Maybe, probably. We're never entirely sure. But that's essentially what it comes down to. There is an issue with the engine. When you burn LNG primarily is methane. So CH4 or methane is 27 times more potent as a greenhouse gas than CO2. So if any of that gas manages to escape, you completely negate any of the savings that you're making by using LNG. You'll see there's another LNG there. Go up a step. Biomass. That's a solution. So biomass, any biological matter, basically we can break down and turn into a fuel. So it can be anything such as waste, kitchen waste. If you treat kitchen waste under what we call anaerobic, so without oxygen conditions, the oils and the carbon-based compounds will come out. You'll end up with something that's akin to a fuel out of that. So you can use biomass to fuel your ships. And it's got a much lower carbon footprint because the biomass has grown, it's taken some carbon out. Excellent, let's use biomass. You'll see that biomass makes it into methanol, it also comes into ammonia, biodiesel up there as well. So there's lots of options for using biomass. Now, if we added up all the biomass that was viable to make fuel on the planet, it wouldn't even touch the sides of the demand for fueling ships. If we then got rid of all the food and planted biomass crops, we still wouldn't quite be there. And we'd all starve. So there's kind of a bit of a conflict problem there. We might be able to get a bit closer using things such as algal biofuels, we call Gen 4 biofuels, using the sea, basically as a production of algal biofuels. But again, you're not going to get enough, at least not at the scale you need ships to run on. You might be able to do something with what we would term as near shore. So these are ships that are running from the coast back in, up to about 200 miles from near shore stuff, maybe. So we go up a bit further. Let's look at things like methanol. It's a bit like alcohol. Well, it is an alcohol. It's a bit like ethanol, which is generally the sort of stuff you find in alcohol. But don't drink methanol because you probably go blind, you might die. You know, it's not great. It's kind of a cousin to that. It's the same principle. You know, if you set fire to rum to find the proof, that's where it. Ever heard that story? The rum, when it reaches its proof, is when you set fire to it, 46% alcohol in burn. But methanol, same principle. You're burning methanol instead of diesel. Again, though, you get methanol from natural gas. That's where primarily most of our industrial methanol comes from. You make the problem worse. There is more carbon locked up in methanol that's been industrially produced from natural gas than there is in diesel. Just burn the diesel. Biomass, same problems we just said. Hydrogen. Hydrogen is sort of held up and flag wave just the solution to this problem. You hear it a lot in the automotive. If anyone's following this sort of the automotive space at the moment, people bang on about hydrogen. Hydrogen is the way forwards. The only emission with hydrogen is water vapor. That's true, yes. You burn hydrogen, it bonds with oxygen, it produces H2O, which is water. Very true. There is a problem. Okay, there's always a problem. I like problems. Hydrogen itself does contribute to climate change. It is a greenhouse gas. Recent report from the Intergovernmental Panel on Climate Change suggests that it has a radiative forcing effect, that is the ability to warm the atmosphere, potentially more than CO2. Doesn't look so great. The other problem is water vapor. It's also quite a potent greenhouse gas. Not fully understood that one yet. If everybody switches to hydrogen in your cars and in your ships, much like we've upset the carbon cycle, there's a potential reaction to introduce more water into the atmosphere, which then has a knock-on effect. No problem. But it's just water vapor. The good thing is it's very clean. 66,000 deaths around the world every year are a result of the shipping industry. Excess deaths just from pollution. So if you can switch to hydrogen, it's clean, reduces that, takes that down. So there's a benefit. The one we want though is this one, the biomass hydrogen or the AER hydrogen at the top. So AER is hydrogen produced by renewable energy sources. So wind power generally or solar. It looks really good. It does look really, really good. Now, 95 to 97% of all the hydrogen produced at this point in time comes from natural gas. The little bit, I've got a colleague I work with, he likes to sort of joke about this. He says that extra 3% is kind of a rounding error, it really exists. But about 3% of current hydrogen production is from renewable sources, from splitting water essentially. It's a very, very energy intensive process. You need a lot of energy and we simply don't have the excess energy in the grid to be able to do it. So again, it's kind of a barrier in the way of this. Ammonia, then, this is actually being used. So ammonia is proposed as a carrier of hydrogen. So ammonia is a carbon-hydrogen formation atom, so it's carrying the hydrogen. Again, there's a bit of an issue here that you're looking at. Most of it's produced from natural gas, which isn't great. If you produce it from biomass, it looks pretty good. Now, I was on a panel with the outgoing head of the MCA, the Maritime Coast Guard Agency, and we were talking about ammonia. His reaction to ammonia was, you try bringing an ammonia-powered ship into Southampton, the MCA are going to have something to say about it, the harbour master is going to have something to say about it, and so are probably the local residents. Ammonia, best way to think about it, you walk past the hairdressers, when you walk past the hairdressers and you get that kind of back of the throat burn, that's very, very, very weak ammonia. It's what you used to dye your hair with. Pure ammonium, it's highly toxic and it's quite nasty and it can be explosive and various other things. It's very difficult to think about and use. Now, it works though. That's the important thing. It works and we can manage that risk. We can use it. Now, if, however, we wanted to switch the entire UK fleet, shipping fleet, onto ammonia, we'd probably need somewhere around about 4 or 5 new nuclear power stations to provide the energy to produce the ammonia. So there's a kind of step up in terms of the chemistry that has to happen as well to produce. Biodiesel we kind of spoke about. Let me get to my personal favourite, and actually what I believe, I'm going to be really controversial. I know some people probably ask me questions about this. Nuclear energy has one of the lowest carbon footprints associated with power production. Also, has one of the lowest death rates associated with megajoule of energy produced. There is an issue with nuclear. One is it's quite expensive. In fact, we don't know how expensive it is because it's generally the preserve of the military. The military don't really care, and they also don't tell you how much they spent on the nuclear reactor on their submarine. It's a very proven technology. Marinized nuclear reactors have been around for well over 50 years. The first civilian ship was MV Savannah. She was produced in 1957, I think, top of my head. Produced by the Americans. Again, though, the cost was never disclosed. So we don't quite know how much this cost, but it is a very proven technology, and actually it's getting better all the time. There are talks from Skunk Labs owned by Lockheed Martin, that they can produce miniaturized reactors and fit the back of the container now. So, this technology, it's the only technology as well that produces enough energy that you can keep the cargo space on your ship equivalent to what you could with that fuel oil. You put hydrogen on, the same energy that's in this bottle, you need 5 times the space to get the same energy in the fuel oil that I've got in the bottle. So you get a cargo ship, deep sea cargo ship, you're now talking 40, 50% of your hull space taken up. Talk to CEO of a large shipping company, they're going to tell you to go away if that's what it is. Or you pass it on to the consumer. All of a sudden, you think inflation's running high now. Let's think about it if we're losing that cargo space. The advantage, of course, is you can do it up once and it's 30-year lifetime, and it just goes backwards and forwards. Big problems, though. Security. How do you make that secure? How do you ensure that piracy is not going to lead to some of those elements falling into the wrong hands? It's a big issue. It's a big potential risk. Another problem, training. No longer do we need what we term as METOs, maritime electrotechnical officers. Part of their training, they basically run the electrical components of the ship. What we need is nuclear engineers and nuclear physicists. It's quite a step. Then there's the perception issue that goes alongside that. If we talk about nuclear fuel, people tend to think of things like Fukushima or Chernobyl, Windscale, there's our one, 3 Mile Island, the American. Disasters on quite large scale. And there is no denying that if something goes wrong, it tends to do it quite catastrophically. However, coal has a per unit generated death rate in the order of hundreds of thousands of people per gigajoule generated when you start accounting for things such as mining accidents, pollution, instances of related deaths. Nuclear, less than 0.1 per gigajoule generated. It's much, much lower. It is relatively safe. But, a number of things to overcome. I'll grab questions right at the end of the those. I know I'm just throwing controversy and a bit of a controversial grenade into the room. I enjoyed it. Like a bit of debate at the end. So, we've got a problem. There are potential solutions on the market. There are things out there, ways we can deal with it. There are challenges to overcome. Paris Agreement 2015 set 2050 as our target date for getting to that 1%. 1 degree, 1.5 degrees climate rise. Okay. To do that, we need 95% reduction mile for mile in carbon emissions from shipping. That's kind of the target we're working to. And that's got to happen in 28 years. The average lifetime of a ship is about 30 years. Challenges, though. Shipping is strangely unique as an industry. I don't know if there's anyone in this room who's ever worked in the maritime industry. So looking around for any nods, there's a few nods. Yeah, it's a bit of it is a strangely unique industry. It has its own quirks, it has its own traditions, it has very much a weight and a gravitas, and it doesn't like to do things fast, it likes to do things in a very measured way. But it's also, its ownership models are a bit strange. So if you have a ship, generally large cargo ships are not operated by the people who own them. So you charter the ship, and charter space on the ship to carry your goods across and around the world. The crew then may be brought in by an agency, but the person who actually owns the ship is kind of subject to that. So we would term as the split incentive problem. There's no incentive for the person who owns the ship to decarbonize it because it's not going to make any more money chartering it out. The market simply doesn't recognize it. And the charterer doesn't really want to pay. And equally, they don't want to pay for the ship that they're chartering or pay higher charter rates simply to have a green ship. The market, again, doesn't recognize it. It's what you might sort of call the landlord versus the renter. Think of it like that. If you're a renter, you don't want to invest in the house you rent. What's the point? It's not your house. Another problem is money. These are multi-million-pound investments. So the Ever Given, the sister ships that were being built, I can't remember exactly how many there are that have been built by Evergreen, but the order was one of the largest orders ever placed in the industry, and it ran close to $1 billion for that one order for a handful of ships. These things are expensive assets. Access to finance, obviously, it's quite difficult. It's quite a restricted market. Again, financiers are not particularly in favour of paying more for a ship than they have to because you want a return on investment. So you're not going to invest in something that's an unproven technology. You're not going to put your money into, say, ammonia if you're not 100% sure that ammonia is going to be the way forwards for the industry. You're not going to put in LNG unless everybody else kind of puts it in LNG. At the moment, heavy fuel oil is a safe bet. Now, the IMO, the International Maritime Organization, estimates that between 2030 and 2050, if we want to meet that target, that Paris Agreement at 1.5 degrees for the maritime industry, it's going to require about $1 trillion of investment in new technology across the maritime fleet. That's a massive amount of money. There was some statistic I was reading about the idea of $1 trillion. If you took dollar bills, so to use the American phrase, and you stack them one on top of the other, you'd reach the moon, and you still have some left over. It's massive, massive, massive investment. There's also a problem with the finances and shipping that a lot of other industries have kind of cross-linked investment potential. If you build a building, the asset can be used for lots of different things. There's a little bit of risk. A ship, it's a ship, doesn't have that ability to cross-link between industries. So you're sinking your money into that vessel. There's then a couple of problems on this side. The IMO is the main regulatory body for shipping, the International Maritime Organization, made up of 174 members, I believe, each one representing a flag state or country. And they come together regularly to discuss various things to do with shipping, things like regulations. 174 people in a room, one of them dissents, vote doesn't pass. So things tend to, as I said, be quite slow, take a long time. Only now are we going through the process of updating things such as coal regs. So coal regs is the collision avoidance regulations. Last were written back in the 70s, modified in the 90s. But it's being revised now. The way IMO tends to work is it's going to goes to the lowest possible denominator. It tends to be retroactive. You're looking at what's kind of on the market, what technologies exist at the moment. Trying to write regulation for something that doesn't exist yet, it's difficult, shall we say. Trying to write regulation, how do we handle ammonia as a fuel? How do we handle hydrogen fuels? How do we safely handle methanol on board ship? Those regulations don't exist yet. We don't know. And that's not the only problem we've got to think about. There are things such as automation, remote ship operation, autonomous ship operation, all these questions as well that have got to be answered that are going through this process. Now, you're going to get disagreement. You're especially going to get disagreement where there are large financial impacts, which of course there are with these kind of things. But there is some good news. The IMO, its long-term 2050 strategy came out probably about a year ago now, pretty much reaching net zero by 2050. That is the aim of the IMO. It was originally 50% reduction in emissions. It was criticised for being too low, but now net zero by 2050. But that in context, importantly, net zero, not zero. So net zero, you can offset some of it. You don't have to stop it. Talk about that for a long time. I don't necessarily agree that's the best way forwards, but it's the way that these things work. But 2050, that's the target we work towards. As I said, 28 years, that's it. Which brings us to this final point. TikTok. Time is running out. I usually try to promise not to be the doom-mongering environmental scientist in the room here. But time is always the problem. Much like the tide, it waits for nobody. Average ship life, 30 years. Average age of the fleet's around 26-ish years at the moment. Ships being built now have to be able to meet that 2050 target. So the ships that are in dock right now, having their hulls laid, those new Ever Given ships that are being built, the Evergreen ships, they really need to be able to use the fuel that you're going to be using in 2050. That's a big ask because we don't know what that is yet. We don't know what it is. The cadets we're training now need to be able to operate those ships. But we're not 100% sure what those skills are going to be. Time is very much against us. And I want to end with a thought. This is how we used to fuel ships. Hasn't changed that much. We still bring a bunker barge alongside. We used to use the same terminology. Instead of lots and lots of men standing there poisoning their lungs with coal dust, we use a big pipe and you can plug it in and it pumps fuel in. But you used to have a bunkering barge would arrive, gangs of men would lift up buckets of coal and tip it into the hull of the ship. If you look at the transition from sail to coal, it was well over a century that it took for that process to initiate. Depending where you draw the line, the transition from coal to oil, about 150 years, give or take, for all the ships to transition across. And we're still burning coal. This is a ship that still runs on a commercial basis, Badger. She runs on the Great Lakes. She is the world's last coal-fired ship, and she's still operating today. 150 years. 28. Gentlemen, thank you very much. It's been a pleasure. I believe we'll reconvene for the questions momentarily. Thank you.
Thanks very much, Laurie. I think we'll definitely set us up for some lively questions after the break. Just a quick heads up. Our next talk is on Monday, the 1st of August. It's Learning from Accidents, Railway Signalling in the UK. You'll probably remember there have been some fairly significant. So, first question I have from Simon via YouTube says, when I drive at 70 miles an hour, I use more fuel than at 50 miles an hour. Does sailing the ship slower reduce fuel usage?
Almost relatively easier question to start with. I thought I was going to get more controversial. I'm sure it does get more controversial. Yes. Next question. No. Generally, what you find with the ship. So the reason your car is more efficient. There's an efficiency in the engine. There's also an efficiency in terms of the drag of the vehicle. That's more pronounced with the ship because water is much more dense than air. Basically, if you've ever been swimming, it's harder to push through water than it is to push through the air. So a ship is breaking through the water. The faster it's going, you get a logarithmic increase in the energy requirements associated with the ship. So one of the most effective things has actually been reducing ship speeds from about 24 knots to about 17 on average. So companies like Maersk, I think, quite a good example of that. They actually reduce their speed. They call it slow steaming, and it reduces your emission and actually fuel consumption and your cost quite significantly because of that logarithmic kick at the end of the So yes, yeah, very, very big reduced emissions. I think there might be a follow-up on that.
Quick follow-up. If those ships are going more slowly,
yep,
are people more likely to fly those routes instead?
Yeah, good question. Probably not. It's not going to add significant time to the transition. If you can manage 6 weeks at sea anyway, then that extra few days probably not going to be a major issue. Probably not. And it's one of those industries where as long as you know roughly when things are going to arrive, you're okay. It's, as we found kind of at the beginning of COVID with toilet paper, I think it's a really nice example of this. It's sold out. Why it's sold out, I never know. It was just one of those fascinating things. But of course, we didn't know that was going to occur, so that lag time meant that you then start running out in terms of the supply chain. So as long as you know roughly where things are going to be, it's not actually a problem. But yeah, air tends to be time sensitive stuff. So fresh fruit and vegetables, some of them will be shipped by air. It's just
yeah. I think this one says, is reducing the volume of trade a viable solution?
This is where we start getting into kind of the philosophy of the problem. If I only slightly crude at the end of this, buy less crap. Yeah, because how much of the shipping of those containers are made up of the small plastic bits of tan that you find inside a Christmas cracker? Not to rain on the parade of any children out there, but Easter. It's an industry where we ship great volumes of air all around the world. Yeah, but you know, just sort of buy less stuff. Yeah, it's a really difficult one, because buying less stuff would mean a reduction in the volume of shipping. It would mean a reduction in the volume of producing stuff. And actually, I said today 2.5% greenhouse gas emissions come from shipping. If you were to buy a block of cheddar, let's use that as an example. If you bought a nice local piece of cheddar or its equivalent from sort of down the road in Winchester, or you had a choice, you could go to the supermarket and buy Canadian cheddar. The assumption is, of course, the Canadian one is going to be worse because it's travelled from Canada to the UK. However, in terms of the product, the shipping makes up a tiny, tiny proportion of its overall carbon footprint. It's far more important as to how the thing is produced, extensively or intensively in terms of the farming method, than it is where it's come from in the world. So on a per product basis, strangely, it's much more about how you make it and what it is than it is about how you ship it. But yes, shipping less stuff or shipping it more efficiently would certainly reduce the volumes of stuff we're just transporting around the world. And, buying stuff you're going to throw away is a whole other argument. I could go on for hours about that, but that's, buy less stuff. You really need
it. This one's a bit despairing, I think. You're saying, is there any hope at all? The only answer is to wait, is to want less, surely, and that won't happen. Give up. I suppose the sort of an extension of that question is, you've told us all the stuff that doesn't work, but you can't teach people. What do you teach people?
Good question. So I suppose when people first meet, I probably come across as a pessimist. It's not pessimism, it's opportunistic pessimism is the way I would describe it. So there is a possibility, or actually no, let's be more blunt at that. There is a fact that the world is getting warmer, things are getting more difficult in certain parts of the world. It's going to have consequences for all of us. That bit we cannot deny. How far those consequences go is kind of up to us. So we need to take the opportunities to try and lay out the future. So just buying less stuff isn't necessarily the solution. There are other technological solutions. I think doing what I do, I have to believe that to be the case. If I didn't, well, I might as well give up now. So yeah, I think buying less stuff, economic rethink is important. I'm going to sort of give my utopian view here. I'm a big fan of Star Trek. There's no Trekkies in the room. But a point where actually the stuff is less important, and actually the thing that we value, I think lockdown showed us this a bit, family, relationships, social value and capital is actually potentially more important. And until we start moving ourselves a little bit more down that route, the buying less stuff doesn't even happen, because that's not the society we live in. But there are solutions. The question is how do we make them happen? And are we willing to make them happen? And actually, if you look again, let's just go back to COVID, I'm kind of using it as my reference point now. We are able to mobilize and do things very, very quickly when we want to. We had no vaccinations for things like the common cold or the related COVID-based diseases. Within 2 years, we did it. We can do these things if the political will and the will is there to deliver it. Don't know if that really answers the question. Just go more.
Yeah. Somebody's saying, do you see any future in hydrogen-fueled ships? I suppose one of the opportunities there could be that in places like the Gulf, where they've got vast amounts of solar power and then they're close to a coast, that's one place where you could produce a lot of hydrogen and pump it in ships.
Yeah. So yes, I do. I think there's a space for hydrogen. It's not necessarily in the deep sea market. That's what I would caveat that with. So we're involved in projects at the moment. We're actually advising a shipyard and an operator in the Netherlands. We're building a hydrogen vessel. That vessel, though, operates in the near shore. It doesn't really go out very far. It operates around the canals around the Netherlands, France, Germany, that kind of area. So it doesn't need to carry very large amounts of fuel. Doesn't need to go very far. It doesn't face particularly high seas and all those kind of things. The biggest problem you've got with hydrogen is it's what we would term its energy density. So how much energy is actually in the hydrogen? So it's a colourless, odourless gas. It It likes to escape from things. And you can kind of squash it. So you squash it right down. Generally, you're looking at about 750 atmospheres, 750 bars worth of pressure. That's what you need to get it down to. We can do that relatively safely. We can actually get it to about 1,000 atmospheres, so really squash it down. Even if you're doing that, so you're running at about 700 bar, you're going to, as a minimum, triple the amount of space you need for the fuel to get the same amount of energy out of that vessel. So the nearshore stuff, that kind of works because you're coming in at least every couple of days, you're coming up with fuel up, you don't need massive fuel tanks. Deep sea, as I said before, your problem is you can't get enough fuel on the vessel without losing cargo space or passenger space. Or at least not yet. I mean, there's talk around things like cryogenic hydrogen, so you take it down to minus 273 degrees, and it becomes a liquid, and you get a lot more in the space. Still need more than you would of normal fuel, but it's better. There are other questions around freezing and stuff. It's very cold. So yeah, I see that there's a space for it, but I suppose there's no one solution. That's really what it comes down to. There will be different solutions for different scenarios, and hydrogen isn't the magic bullet. It's useful as an engine carrier for certain situations, and other technologies are better suited to other situations.
One quite topical question, I think, for a community that's not that far from the port. Mm-hmm. In fact, we've had a talk in the past on the impact of particulate pollution actually affecting Winchester from the port in the past. The question was, how often do ships get their energy from onshore electricity when in port? Should it be mandatory?
In Southampton at the moment, never. I think there are talk of installing what we would call cold ironing facilities in Southampton. I may be wrong, it may already be in existence, but at least until very recently, never. Certain places of the world it is mandated. So California have a law which mandates all ships must be capable of taking that kind of plug in the side. So when we talk about cold ironing, imagine you're plugging a cruise ship in. It's not like kind of a 3-pin domestic socket. It's massive, multi-phase, multi-megawatt system that you're plugging into the ship. Yes, personally, I think to answer the question, yes, it should be something that probably we should be working towards. It certainly deals with a lot of the emissions around the port. If you look at Southampton as an example, there are areas of Southampton much more heavily polluted than other areas. So if you look along sort of towards the geography right now, I think it's towards the west, so looking towards Redbridge, Millbank, that kind of area. Tends to be much more polluted, but it gets the braving wind. So of course it gets the blowing of all the ship emissions that are coming across there. There are areas around the world where you can actually map differences in life expectancy related to air pollution. It's quite phenomenal. The UK has a difference in life expectancy between areas, not solely on pollution, but it's a contributing factor of up to 11 years between some regions, which is quite amazing. You think such a developed nation. But yeah, certainly would help. And as you say, you can pick up particulate matter in some of the certain smoke that's coming off ships here in Winchester. So that's why I live on the Isle of Wight, we're downwind. So.
I did see a story a couple of years ago about one of the first electrically powered freight ships. It was Coaster. It was in China, and it was moving freight about 50 miles up the coast, and it was running entirely on batteries. It was moving coal. Guess where the power came from?
I'm going to jump on this one because this is one of the amount of times I hear this put forward to me is, you've bought an electric car. Yeah, I feel good about it. But where does the power come from? It comes from coal. Well, some of it, depending where you are in the world. So if you go to Belgium still has quite a high coal-fired power station next to it. Go to France, it's got nuclear, so it's got carbon footprint. We tend to rely on gas at the moment. Those big thermal power stations are a lot more efficient than your car is. I can tell you that. So they have a lower per unit energy. The other thing is electricity is much more efficient in terms of transferring itself between things. You burn fuel, you're getting about 30% of it most, because you're limited by thermodynamics. You can't get any more out of it whatsoever. Electricity runs in the order of 99% of it. If you get a really efficient transfer, you get it all. So you don't lose the energy. So it is much, much more efficient as electricity, much, much more efficient. But yes, there is a need to further improve the power supply and move off of fossil fuels in the power supply to then use the energy electrically, locally, to power things like your car or your ship. And the irony is not lost that you're moving coal around using an electric ship. But it's better than burning that stuff over there. I think maybe there's a follow-up coming up there.
Yes, this is different. About the safety of different forms of energy. You mentioned in passing that the number of deaths in nuclear, I think you said,
I think it's below 1 per gigajoule. So.
I'm happy about these figures because there are very different nuclear accidents in children. I'm wondering which forms of death.
Yeah, so it's the study. I think it was
Can you repeat the question?
Yeah, of course I can. So thinking about the figures for number of deaths from energy production methods, I think that's kind of where we're going with this and how those forms are worked out. So especially with nuclear, there are a number of ways that might lead to death, for example. Is that correct?
No, we don't know. I don't. Because the obvious way to nuclear accidents is one is by gas, another is by
yeah.
And the third is by long-term tumors.
Yeah. Yeah.
And that's
yeah. So there are some studies, which is where I think the IEA got their data from. I'd have to look up the report to find those numbers for you. But you're right with nuclear. So you've got the direct stuff based on the accident. Say at Chernobyl, there were some immediate deaths from the fire. So the deaths related to that. There were then deaths within a number of weeks. The people who went in to try and put the reactor under control. They didn't last more than a couple of weeks from acute radiation poisoning. There were then a number of deaths that followed on, and those populations have been tracked since the disaster. So there are deaths associated with nuclear. That's not in question. What it is on a per unit of generation of energy, it is significantly lower than if you're comparing it to coal. So coal, there are multiple ways to die from that. Let's just, put that in context. So a mining accident, for example, or dust, or pulmonary disease, or cancer, or even radioactivity from coal. If you work in a coal mine, you're exposed to radioactivity. There's also the question, if we just take transport globally, 190,000 excess deaths as a result of exposure to particulate matter from transport. So, these figures are not, it's not kind of pointing fingers and counting people. It's working out what they would term as the excess. Like we would talk about COVID, for example, we talk about excess deaths in the population. It's more and above what you would expect there to be as a result of that particular thing. That is then normalized by unit energy generated. And it is because nuclear is so efficient and because it's reasonably safe when it's done properly, that number is much lower than coal. So I say I can get you the exact figures. I can happily share those. So.
Alan, I think we'll park that one there because that's not something we're going to be able to answer tonight.
Yeah. I mean, there is a huge debate around it before. I think it's something that we could talk for hours about that.
Yeah. So somebody's asked, you said that ships last 30 years or so. Is the recycling of ships sustainable? What is the environmental cost of recycling? I know that has some interesting dependencies on where it's done.
Yeah, so depends what you mean by recycling. Not by recycling, by sustainable rather, because there are a number of facets to that. If we take the environmental side of it, it's certainly better to recycle it than it is to leave it to rot as a wreck. Let's start at that point. So historically, you just scuttled ships. Something was the easiest way to get them. We kind of thought it was the easiest way. Recycling them, of course, you recover the steel, you can recover a lot of materials in it. You've got a lot of contaminants associated with it as well, you need to deal with. There are certain components you can't recycle. So certainly let's think about things like certain plastics you can't recycle. Certain bits of the metal, if it's contaminated in certain ways, it has no value, but a lot of it does. Now, the kind of, suppose the issue you're alluding to there depends a bit on where it's done in the world. A lot of ships to recycle in things like the coast of Africa. So a ship, to recycle it, get on board, you put it into full throttle and you run it at the beach. As fast as you can, it runs up the beach and it sticks inside. It is then cut to bits and chopped up and dismantled. That's kind of the most common way of breaking a ship apart. There are serious social elements associated with that. It's incredibly unsafe. It's really not a very pleasant occupation. And there's an argument to say as well that we're pushing the problems that we have created in many cases onto people who then feel the effects of these issues. So certainly it is something we think about. Something I think would be interesting is when we start using new technologies. And I'm just going to literally go back a little bit to I think it was Alan's point there about nuclear. That presents, if that's the route you go down, you've got a whole other question around recycling that starts coming in, is how do you safely decommission that? We're quite practiced at it, but you can't go running that at a beach at full pelt to then try and decommission a nuclear reactor. It's just not going to cut it. But yeah, certainly an important part of the puzzle. But I should say as well, the average lifetime of ships, 30 years, a lot of ships are a lot older than that. Some ships run into 50, 60 years quite happily. What tends to happen is they get sold. So a ship will start running the European market, it gets a bit older, reaches like 25 years, something like that, it gets sold out perhaps to the Asian market, then it gets sold on again, and they gradually make their way around the world. You end up with pockets of very, very old fleet around the world. So it's not saying that at 30 they can't get chopped up and thrown away. It's just sort of the expected lifetime, I suppose.
Yeah, there's a couple of thoughts around that, because one is we know that recycling steel is much more carbon efficient than working from ore, so it can be used with an electrical process, which is one part of it. I suppose there's also an issue of when you're talking about the ships being kept going for 60 years. I know it always used to be the thing, and I guess they haven't got away from it entirely, is that old ships were more often lost at sea, and then you've got some very significant pollution issues.
Yeah, I mean, that's a really interesting point to it. So I was looking at the stats, I can't remember exactly how many there were. I think it was 7 last year, off the top of my head. My colleagues in the room might know better than I do, but major instances of wrecked ship. It's actually a lot lower than you'd think it would be. You go back 30, 40 years, you were talking many, many, many more instances of wrecks at sea. So we're getting better at not wrecking ships. That's kind of good. The problem with something like that is ships are getting bigger and bigger and bigger and bigger. So something goes wrong, it tends to go wrong quite catastrophically. So Costa Concordia is an example, Ever Given is another example. And trying to sort of recover from those disasters is getting harder. So not to go on it too much, but if you think about the way the insurers work, they're insuring the ship for that instance, basically, that it would happen. Either it's a write-off or it has the money to recover it. To recover a ship, you need some quite heavy equipment. But that equipment as an investment doesn't really do anything most of its life. It's just there to pick ships up off the ground. So very, very, very big power tugs, for example. There are only 2 or 3 companies in the world now that can deal with these really big ships. They just really don't exist. So the capacity is getting less. So there's a big question emerging around, as ships are getting bigger, are we ready to deal with some of those mega ship disasters if they were to happen? Or I say if, when. It will happen. An accident is one of those things. It's always waiting to happen. You're just trying to avoid it and minimize the chance that it's going to happen. So there's a big, really big question to answer around that. And the environmental impact of those things happening is getting bigger and bigger and bigger, and the risk gets bigger because the ships get bigger. The amount of fuel it carries gets bigger. The amount of cargo it carries gets bigger. You're talking about ammonia or nuclear, if we want to be really controversial. Those kind of instances could be catastrophic. So, some big questions to play with there.
And the last question we had, which I will embroider slightly, they're asking what types of ships are or what propulsion systems are evergreen building now? It's sort of a rider to that. Is there any sort of prospect of any kind of hybrid shipping? You talked about sailing being a problem if you ran out of wind, but can you combine wind propulsion, say, with other, so that you're using less fuel, and indeed any other kind of hybrid technologies within the space available?
Yes, you can. Let's think about this a bit more deeply. So there are a number of examples out there. Much like you have a hybridized car, you have what we would term as a multimodal clutching system. You can do that in a ship. So we worked with another vessel that was a hybrid electric diesel. So it had a small diesel engine, but also had an electric battery bank, an electric engine, and she could run on either. Just would switch between using the clutching mechanism on the ship. As you get to bigger scale, it gets a bit more difficult. It goes back to that problem of energy. So finding enough energy. There's some ideas being thrown around that you might use, say, electric to bring the ship in close to its destination, or hydrogen, but then using fuel oil for the rest of the journey. It's worth pointing out that a lot of ships have what we would call a multi-fuel ability already. So they run on that nasty stuff over there for most of their journey. But as they start coming into, we term SECA, sulfur emission control area. So an emission control zone, you use low sulfur fuel. Basically. The engine switches over, starts using basically it's more like diesel. So that technology exists already. Some of the fuels are dropping as well. You just put them into the engine, you can do that. You just swap over, and it just changes the pipeline. The fuel that's coming in, it just burns straight away. In terms of things like sail, there are examples of that already happening. So there are ships with deployable kites. So like you see a kite surfer, the big kite, the ship deploys a kite on the front, and that takes off some of the propulsive power of the kite. My point about cadets not being able to sail per se anymore, it's taken away because of things like AI. So an AI looks after that sail. It's just a completely automated process. You push a button, sail deploys, push another right, comes back. There are some examples of deployable fixed sails, ships that put up these sails, and that gives them a little bit of propulsive power. Nowhere near enough to power the whole thing. It's important. There are examples of some that use the Magnus effect. So basically, you get a spinning cylinder, you spin it in air, and it creates a vortice effect. It's a bit like a plane wing. It will pull the ship along. Only works if the wind is really in the right direction, a bit like slow. But that can shave a few percentage points off of the fuel. So it's all these things kind of together. So one of the principles we're working to is there is this idea, there is no one solution to this problem. And if first thing you really want to think about doing is reduce the fuel demand in the first place. Because if you reduce the fuel demand, then things like hydrogen becomes more viable. You need less of it. So ways you might do that, you can reduce hull resistance. There's some things you can do that. You can blow bubbles under the hull, that lifts it up slightly, reduces your drag on the ship. Certain vessels, you can make them plane a bit better. You can lift them up on foils. There's a few things you can do to reduce that resistance. You then might put on Magnus rotors or sails or something like that, reduce it a bit further. If you cut 10% of that out, then all of a sudden you need 10% less fuel, so then you might get a use of hydrogen in there, which reduces the HFO. So yeah, they are viable technologies. They're not going to replace the need for the fuel, but used in conjunction with lots of other different bits of technology, then you start getting to a point where these things start to become more and more viable. So it's again, to go back to my original line, I think it's no one solution. It's going to have to be a multitude of solutions and rethink to get this to work properly. But it's what keeps me in the job.
Yeah.
Thanks for another question.
What's the last one?
Oh, wait. Going back to your earlier point about reducing demand, which would stop the amount of shipping going, do you think a move towards forcing products to be more repairable rather than single use would help to reduce the amount of goods that are moving? If, say, a washing machine goes wrong and it only requires a circuit board replaced rather than a whole machine that has to come across on a ship for a new one.
Yeah, so would increasing repairability essentially reduce the demand and then also have the knock-on effect of reducing shipping demand in there? Potentially. There's kind of a lot of study in this, and there's a big move. I think it was a European piece of legislation went through relatively recently, the right to repair. I think it made its way into UK legislation as well. But the idea that if let's take it like a mobile phone these days. If you've got a mobile phone, it's pretty hard to fix it when it starts to go wrong because they're just nice sealed units. They don't like being repaired. And we use the example of washing machine. A lot of washing machines, you can't repair them anymore. I remember as a kid, we had the washing machine repairman. We kept our washing machine going for about 15 years. Just an old hot point thing that he'd come and fix. And you try fixing one now. But it certainly would, I think, potentially reduce demand. I say potentially because there's an added piece to this, that the washing machines now are much cheaper than they used to be. So it's almost as easy just to go out and buy a new one as it was to get it repaired. And there's that balancing act, especially some products. And a phone, I think, is another good example. But your phone goes wrong after 3 years, and well, I wanted an upgrade anyway. So you don't repair it. So there's this questionable nature to it. The other side to it is it's you buy the repairable machine. So I'm trying to do it without saying brand names all over the place, but let's buy a high-end machine from a nice retailer down in Southampton in the multi-story thing that costs a lot of money to go into and has its green colours. So you go in there and you buy your nice repairable machine. It's probably going to cost you more initially than buying your £100 machine. It's going to last you 2 or 3 years. So if you got the money to do it, I think it's a really good idea. And actually, it's something I would really advocate. Is buy once, cry once. It's principle for life. Buy it once and worry about it once. Spend the money. And in the long run, it probably costs you less. That's the weird irony of it. But if you haven't got that money in the first place, you can't afford to do it, and you'll have to keep buying a washing machine every 4 or 5 years. So there's always going to be a place in the market for that cheaper, less repairable part. And it's a difficult one to do because I think it's easy to kind of say, take another example, take shoes as an example. It's easy to buy a £10 pair of shoes and buy one. They're not going to last you for 6 months. You buy a £300 pair of shoes from Churches or something like that, it's going to last you a lifetime because you can just keep repairing them and fixing them and send them away and they come back. But you've got to have the capital to outlay. So it's easy to be poor when you've got loads of money. This is my point. So I think, yes, it's a really valid point. I think it's certainly something that should be there. If you buy a mobile phone, you should be able to repair it. Yes. You buy a washing machine, yes, you should be able to repair it. But there's always going to be that little bit of the market that needs filling until fundamentally we change the way we run the economy or do business. So it's no easy solutions again. But I think it's a really good point.
Because there was a follow-on point to that. There was a debate about where jobs were going to come from in the future. And if automation is going to make it difficult for people to work in manufacturing, the one thing automation can't do is repair. So that becomes a source of jobs. Yeah. I mean, again, I think we could debate this for ages, the idea of automation and things.
You couldn't without ships.
I mean, ships are going automated. It's already happening. We see it now. The first ships are being automated. I think one of the things with that I always think about, if we take the ships as the example, it's the thing I'm most familiar with. As we automate ships or make them remote, true automation, a computer making a decision about the ship isn't going to happen anytime soon. It's a long way off. There's going to be a human in the loop for a long time. The job is going to change. It comes ashore. Actually, people aren't going to sea. There will still be jobs, but they'll be different. And actually, there's a lot of opportunities attached to that, which is that if you imagine, so if you have an accident as a seafarer and you suffer a severe back injury and it affects your ability to walk, you no longer can go to sea. That's it. You're going to fail your medical. You can't do it. You get diabetes, you get type 2 diabetes, you can't go to sea. Career's over. However, if the career is ashore, it's not anymore because that technology of automation has made that job an ashore job. It's a different job. If you get family life, work-life balance, it changes a bit. So, in terms of the automation, I think there will be jobs, and I think you're right, the repair aspect is one of those pieces of it. I don't think that the human will always go away, but certain jobs will go away, like always has done throughout history. The first industrial revolution, people were up in arms and protested because these vile steam monsters were coming and taking our jobs, and we adapted, we as well. So I don't know if I wandered off point there on the question, but I think in one respect, yes, certain things will disappear, and actually making things repairable, yes, it opens up niches, it changes the nature of the economy, things will change. The flip side is we produce more stuff because it's automated and it's cheaper, and then we all buy more and we have more ships. Just, there's potential that goes the other way.
I think we've got time for one last.
Yeah, I think there's one more.
Just going back to Evergreen.
Yeah. Yes.
It's pretty important what they actually are doing now. You said all the data alternatives. Whether they are doing.
So So primarily they're running on HFO. That's what they're running on HFO, heavy fuel oil still.
So the ones they're designing now.
Yeah, are still running on that.
So they will be.
And they will be. Yeah. So some of the fuels I showed you are what we would term as drop-in, so you can use them in an internal combustion engine. So we've got some colleagues in Belgium who they have a large engine, the sort you would find on one of those huge dump trucks using quarries. So they took one of those out to an experiment, and they're busily injecting hydrogen into the mix to see if you can increase the hydrogen and reduce fuel. Basically, they're working on the basis we'll keep going until it blows up. We'll see whether that's how we'll find the ultimate point. So there are things you can kind of do with that tech, but a lot of the ships have been laid out. There is no alternative right now. There just isn't anything out there. There is interest. There's a company in Southampton who just launched a 78-metre vessel that's capable of taking ammonia. But it meant a complete redesign and restructure of the ship and the way the fuel tanks are laid out and the engines are laid out. And that's expensive. It's, as I said before, you're taking a bet on the market, doing something. So most of what is going down now is still based on current technology, and it will be for the facility. So, and then there's a big question then, and a lot of like the projects we're working on about retrofit. Can you actually retrofit those vessels with something new? Can you, if, for example, new battery technology comes on in the next decade that is hugely more energy dense, then actually, how do you retrospectively fit that into the ship in a way that is safe and doesn't upset the balance? So, but yeah, to answer your question, it's the stuff. That's what we're using, because that's the known technology, it's the known quantity, and it's available right now.
But going back to the 19th century, locomotives carried their fuel in a tender pulled along behind. Could that be a viable option for some sort of fuel interchangeability, or is the drag prohibitive?
The principle sounds right, I think, with those things. The problem is, as soon as you put another boat behind the boat, remember that logarithmic curve, you're increasing resistance and increasing drag. It's essentially the same as just putting it on the ship. You're having to pull that through the water. There is some
modularity.
So there is some talk about basically sort of changing the way we're shipping. There's some ideas for reports, but you have kind of more hubbed shipping. So big deep sea vessels that are moving stuff between hubs, and then much more small feeder fleets that are running off much more renewable fuel. It doesn't fundamentally solve that problem in the middle, though. You're still going to be suffering with that. And it's the problem just goes back. There just is nothing on the planet that is as good as holding energy as that stuff is just there. That is really, really good at holding energy and being very, very efficient at doing so. It's cheap. It's still, I know right now petrol's hugely expensive, but it's still cheap. That stuff, really cheap. So, if there are advances in the battery tech and things, we get much better batteries, then maybe we start going to those spaces.
Oh, I think we better bring things to a close. Dr. Laurie Wright, thank you very much for a very fascinating talk and discussion. Really enjoyed that. So we will be back on Monday, the 1st of August, we hope. Circumstances being favourable. If not, we'll still be there online anyway. A sweet jar on the side if anybody would like to contribute towards the venue cost. We have had a